My pleasure to introduce CJ Begalke, and it's actually a really good crowd for AGU week, so that's good. And so CJ went to Creighton University where he studied atmospheric science. He graduated in 2016. And one summer, I think this is interesting, he spent the summer in Colorado working for the NOAA Space Weather Prediction Center, studying electrons in the ionosphere. And he came here in, I think it was fall 2016 to work with me. And so for his project, he's done a really challenging project, I think, and over the last few weeks, it's involved many last-minute changes and updates, and including lots of suggestions from me. And what I appreciate is that CJ is really, every time, was always willing to try the new leads, and I think it really enabled him to. He really covered a lot of ground over these last few months. And for his talk, he's going to be talking about interactions between the zonal flow and the eddies. And this was actually my first project when I was in graduate school. And this methodology has been used many times since then. And what CJ is really going to show us here in a nutshell is how we've been doing it wrong for these last few decades. So take it away.
Thanks for the introduction, Dave. Let me know if anyone has trouble hearing me. I didn't think I would need a microphone, but if that's the case, just holler, let me know, I can speak louder. But again, as Dave mentioned, thanks for everyone for coming. I know it's a busy week, end of the semester. A lot of people are going on AGU, so I appreciate everyone coming out for this talk. So the title of my talk is Quantifying the Role of Eddy-Zonal Flow Feedback on the Zonal Wind Variability using a two-mode approach. And I'll get into all the different aspects of this kind of wordy title as we go. So just a brief outline of what we're going to be doing in this talk. We'll first define the zonal index and the annular mode. They're two terms that we'll use a lot and come up in this talk. Our motivations for why we're doing this research. The first one is that we've seen in the past, there's a poleward shifting jet. It shows up in climate models, and it will show up continually in future model runs. So it's important for us to get an understanding for the zonal wind, the jet stream, and understanding what's going into the variability within the jet. I'll also just mention a few impacts on the climate that we get from a poleward shifting jet and how kind of everyone can kind of understand why it's important. And then I'll list the objectives of this research. Our main tool will be EOF analysis, and so I'll introduce that for those who maybe don't have as good of an understanding of what EOF analysis is. And then our first step is we're going to use a synthetic data set as a kind of proof of concept. We're going to use this, as I said in the title, we're focusing on identifying the feedback parameters on the Eddy-Zonal flow. And so we're going to use this synthetic data set to help assure that we can obtain these feedback parameters, and then we're going to use these feedback parameters to also back out a no feedback case so that we can assess how much these feedback parameters affect the zonal flow variability. We're going to use interim reanalysis. We'll separate into seasons so we can see from season to season if there's any big differences. And then I'll finish off with kind of the main points to take from this talk. So just a brief definition of zonal index. Rossby has been studied this in 1939, studied how fluctuations of zonal circulation lead to a displacement of atmospheric centers of action. That's kind of a mouthful. We'll understand these atmospheric centers of action as the zonal index, or also known as storm tracks. The zonal index refers to the dominant mode of variability. And Rossby determined a high and low index pattern, where high index means the jet is shifted poleward of its mean position, and the low index when it's shifted equatorward. And we're going to be focused on this high index of the high zonal index. I just showed on the right here, just kind of an annual mean conditions of the U wind. You can see where the two jets are in both the north and southern hemisphere. But I highlighted the southern hemisphere because that's what we're focused on in this talk. So like I said, the dominant mode is this zonal index, but it's also known as an annular mode. There's one in the northern hemisphere, the northern annular mode, which also goes by the Arctic Oscillation. And then we have the southern annular mode, which is known as SAM, and that's what we're focused on for this research. Now these figures come from Lorenz and Hartman in 2001, and this just goes to show kind of how well aligned. We have the zonal mean, the annual mean zonal wind up on the top here. And you can see this mid-latitude jet centered at about 50 degrees south. And if you were to transpose this right down to the first EOF, which is the what we're going to be using these EOFs later on, this just shows that EOF is centered at 50 degrees as well. And these contours, positive contours, is to the poleward side, and we have negative contours on the equatorward side, and this is this poleward shift of the jet. And EOF1 and this other figure is when we have we take out we vertically average. And you can see the EOF1 is determining the north-south shift or poleward equatorward shift of the jet, and explains 43% of the variance, but we'll get to that when we go into our EOF analysis. But this kind of sets the tone for the rest of the talk. So where do we see these poleward shifts in the jet? And I just want to go through a few examples of literature that show this poleward shift in the jet, just to make sure and hit home that it's constantly showing up in our study of the atmosphere. So we have the anomalous angular momentum plotted here, positive contours and positive shading. These are showing positive, these are negative anomalies, and you can see how these trend poleward in both the southern hemisphere and in the northern hemisphere as we shift poleward. These anomalous angular momentum anomalies kind of denote the jet poleward shift in the jet. And this is an example from NCAR analysis from 1990 and 1992. Here's an example of the poleward jet shift in general circulation models. This is from Lorenz. I'm not going to get too in-depth as to what's going into this plot here. But in simple terms, we have a control run for the center of the jet in the northern hemisphere. And we have a situation where we've reduced the friction. And it stands to reason that if you're going to reduce the friction, you're going to strengthen the jet. And we see that when you strengthen the jet, we shift that poleward. So where it's centered right along kind of just over 40 north, now it's up towards 50 north, where the center of that jet is located. Another example of this is in Lorenz 2015, where they run multiple perturbations affecting the jet. In the background, you see the shaded mean conditions of the jet, and then what the jet changes to, or the anomalies once you perturb the jet with these specific changes. I'm not going to go into depth on each one of these, but up in A, it shows a decrease in the friction of the zonal mean U wind. We see forward shift. We see this occur in every case. If you were to increase the pole to equator temperature gradient, we see a poleward shift in the jet. And we see this constantly all the way through these GCM examples. And again, we see it even in CMIT 5 multimodal ensemble. We see this poleward shift of the jet. Again, I don't want to kind of beat this into the ground here, but this just goes to show that we see this in the southern hemisphere, and we're going to zonally average our analysis later on. So we're not going to look at different regions, but in this example, in Barnes and Pulvani, they actually broke this up into the North Pacific and the North Atlantic regions. So you can see this even if you break it down into different regions.
I've got a question. I don't know if it opens the Pandora's box that we want to immediately shut, but when you talk about the jet, this is a subtropical jet, correct? Or is it a
mid-latitude?
Okay. Well, so there are two principal jets. I can speak to the northern hemisphere, and I imagine the southern hemisphere is also true that you have the subtropical jet in the northern hemisphere, as an example, is a fairly steady feature, and then you have a much more wavy mid-latitude jet. when you do the averaging, does one, what's left over when you've done it, when you do these zonal averages over time? What stands out in that average? I mean, what you're showing?
What do you mean?
It seems to me that the steadier part of the flow, the zonal flow, that's going to stand out as going to be the profitable jet. I was curious, what does that say in the experiments that are done with that change the temperature gradient, change friction, et cetera? Do they have similar impacts on both the polar as the profitable jets or mid-latitude as the profitable jets?
I'm not sure I can speak to that. I don't know.
Okay, well, we can come back to it.
I mean, yeah, maybe I'll get to it after. So yeah, so I don't want to spend too much time on this, but this just shows that we have the polar shift in the jet. And just a few impacts, kind of what this has on the climate and just kind of how we can understand this. Polar shift in the jet generally leads to a polar shift in the precipitation and wind stress. You see a reduction in the sea level pressure at the poles, increase at the equators. You also see a widening of the tropical belt, which can lead to a lot of shifts in ecosystems, agriculture, what have you. Over on the right here, this is just a positive phase of the Arctic oscillation, and we can see how the jet affects the, when you have a positive phase, it affects, the U.S. gets warm winter, Mediterranean gets drought conditions. So there's these effects of the jet all the way around the globe whenever the jet is shifting forward or equatorward. Again, we see this in the southern hemisphere as well. Just around Australia, the location of precipitation changes the southern annular mode as well. So our focus here is going to be to identify the Eddy-Zonal flow feedbacks for two modes. It's been done for one mode. We're going to add a second mode and attempt to identify these feedbacks. We're going to use lag correlation analysis to kind of visualize this, but again, the main tool we're using is EOF analysis. We're going to quantify these feedback parameters, and then once we have these feedback parameters, we can remove the feedbacks from the system to compare an actual case to a no feedback case, and then come up with the idea for how the feedbacks affect the variability, because we'll be comparing a no feedback case to an actual case, and the difference between the two, we can see how the variability is changing. We'll also test the importance of coupled versus uncoupled, where EOF1 and EOF2 interact versus if EOFs are independent. Like I said, previous studies only look at the uncoupled case here, so we'll find that these coupling these EOFs and the feedbacks are very important. So just a little background on EOF analysis. So it's been used since the 1940s, and it's a useful tool for a number of reasons. It describes the variations of complex field with a few functions and time coefficients. It works well with gridded data. It's agreeable to physical interpretation of complex processes. And as we know that the atmospheric analysis is challenging when you're dealing with propagating and stationary features, and EOF analysis attempts to combat this by finding time and spatial patterns within our data. So this just shows, EOFs are structures in the dimension that explain the most variance. So our goal is in a data set, we're trying to pick out wherever the most variance is occurring. The principal components are the complementary structures in the sampling dimension. EOFs and PCs are orthogonal, which means they come to right angles. And a common example of EOF analysis that even if you aren't super familiar with EOF analysis, I'm sure you've heard, is that ENSO is an example of this when it comes to sea surface temperature anomalies, where EOF analysis picks out the dominant variability in sea surface temperatures, which is ENSO. So kind of the core equation for our research is this, the momentum budget equation, where we have here. And if we vertically average and take the zonal mean, it simplifies to this equation, where all we have is the momentum flux convergence minus and then friction, and those two make up the zonal mean zonal wind. And we'll simplify this simpler equation on the next slide. And we see that by this equation, we're going to see that M forces U in our data. So we're going to start with this synthetic data. We're going to kind of make up this data set using this momentum budget equation, which is just a very simplified equation, but it helps us we can specifically identify where the eddy effects are by using this simplified momentum budget equation. So in this equation, U is just the PC of zonal wind. Again, this synthetic data mimics our principal components that we'll get from our EOF analysis later on when we do the EOF analysis of our actual data. So in these plots, or in these equations, the U is the PC of the zonal wind, not the actual zonal wind in this case. And then MR in this case is the eddy momentum flux convergence. But we start by simply having the eddy momentum flux convergence be random. It's a random eddy forcing. We have this friction term, which is on the right here, and we set tau to be 8 days, which is the damping rate of friction, which is reasonable in a vertically average case. So as you can see here, the M forces U, but there's no clear way for us to see that U forces M. So we're going to look at the lag correlations of this case to kind of see what we see in the synthetic data when we have no feedbacks present. And we know that M forces U, and we can see that here in the lag correlations. They show us this concept. Like we said, M is completely random. It's a randomly forced eddy in this case. And so obviously at leg 1, it's 1, or at leg 0, it's 1, but then every time else, there's no correlation between M and any points surrounding M. U depends on M based on our momentum budget equation. And so U has this persistence that drops down near 0 by the end of our time lags. But there's definitely an impact from M onto U. And we see this pretty clearly when we cross-correlate these values. And we have high correlation values when M is leading U. And we would expect that because we have M forces U. And so we get these high correlation values that at these negative legs. But if in positive legs, U leads M. And we know that based off of the way we used our momentum budget equation, that there's no memory there for U to affect M. M affects U, U doesn't affect M, and that's what we see here. There's zero correlation when U is leading M. And that's all stuff that we would expect. So we're using this general momentum budget equation to kind of just assess and see what we get when we look at these lag correlations. And we're going to step through here. And now we're going to add feedback. We're going to impose our own feedback onto this situation. Now, as I mentioned earlier, the single feedback case is the only one considered in literature so far. It's been used a lot of different times. So we're going to see what happens when we add this feedback to our synthetic data. And we see here that our equation 1 that we used previous changes just a little bit, whereas now this M has that pure random component that we had previously, but also has this AU term, which A is the feedback parameter, and U is our zonal wind. And so now you can see how we're adding a feedback parameter. Previously, M forced U, which M still forces U in this case, but there's some relationship here that we're looking to see. We're adding this feedback parameter. And when we look at the lag correlation analysis, we'll see how this kind of affects our lag correlation plots. So if we look at the persistence here for the autocorrelation of U, which is just U with itself, when you have no feedback, the correlations are lower. But when you add a feedback, we raise these correlations just a little bit because there's this, now we have this term, this feedback term, that is adding to the persistence of this U. And if we look at the autocorrelations of M, we see this occurring as well, and it's not as clear. Now we could run another experiment. We could bump up the feedback parameter, and we could probably see this more drastically, but we see it here, so I'm just pointing out that when you add a feedback, it doesn't drop all the way down to 0 as we did before. There's some memory there in correlation between U and M. And so when we cross-correlate these, we get an even clearer picture of this side where U leads M. So now, as we saw before, M leads U. We have these high correlation values. That's kind of to be expected. And now we see on this side, where U leads M, there is an effect now because we built in the way that U feedbacks into the system, there's a positive correlation at these lag values positively. And this is the feedback that we're attempting to determine in this analysis. We're not focused on this left side as much because we know M forces U. We're looking at this and trying to assess how U leads and forces M. So this, like I said, this research kind of stems from Lorenz and Hartman in 2001, and this is from their analysis of just a single feedback case. So you see in the, they use Z, we use U, so it's just a terminology difference here. But in this Z, these correlations drop down, as we saw before. In M, we have a negative, or we have a near 0 correlations at these long positive legs. And these negative correlations right at low legs, we're not going to focus on for this research. These are actually still being studied. And these turn out to be transient terms. A transient effect, we're not focused on this. But we're looking at this positive, we're looking at these positive legs. And if we go to the Z and M cross correlation, we see this feedback show up at these long positive legs from about 7 to 20, roughly. And it's this positive feedback that we see where Z leads M, in our case U, is affecting this M eddy term. And our goal is to kind of identify this term, quantify it, and see how much of an effect this feedback has on variability. So we continue with this synthetic data, and we decide we're going to add a second mode to our synthetic, because that's what we're going to use with our reanalysis data later on. So we add these feedbacks, and we get this kind of new equation here, where you can see how it all stems from that initial equation, except we're adding these different feedback parameters. We use these feedback parameters here. We use, these turn out to be roughly about what they are in our analysis, so we're just going with, you could run this with different feedback parameters, but again, we're using this as a kind of proof of concept. We want to see if we can set these feedback parameters and see if we can back them out correctly later on, and then see what effects they have on our variability. Here's the autocorrelations, and again, I'm not going to beat this down too hard, but we see similar autocorrelations that we saw previously when we had the one mode for the two modes. U2 drops a little bit negative at long legs, but again, we're not focused on these long legs. We're focused on these kind of legs from about 7 to 20-ish, 7 to 21. And again, we see in the M, there's slight positive correlations at these short legs. But then we can get a little bit more information when we start looking at the cross correlations across these two modes. Okay, so if we look at cross correlations of U1 and U2, we see that this ultimately shows forward propagation. We see positive U1 leads into positive U2, and we get forward propagation when that's occurring. U2, U1 is just the same, is kind of the opposite order, so we're not going to focus too much on this as we kind of progress through.
So just to be clear here then, like U1 would represent a shift of the jet or an extension of the jet?
the U1, which U1 is, in our case, this is like the mode 1,
Yeah,
which is the north-south shift of the jet.
okay.
U2.
Okay.
Okay, and we'll see how this comes into play a little bit more when we look at the EOFs, we look at the EOF plots. And then we have these other kind of relationships between M1U1 and 1U2. And again, we're looking for feedbacks at these kind of positive long legs where it's about 7 to 21. And we see significant positive correlations in M1 and U2, small negative correlations in M1U1 and M2U2, and then negative correlations here in M2U1. We'll go into more of this when we get to our other analysis, or seasonal analysis. But this just shows kind of what we would expect when we get to later on. So once we've run our system with, or created our data set with these feedback parameters, then we want to make sure we can correctly back them out. So we impose our feedback parameters, and we have this equation here. And if we multiply it by U1, sum together, and we get the covariances, we do the same for U2 because we have to do both modes, and we get a much more complex set of equations. We use these equations to solve for each of these parameters because we know the covariance of all of these other terms, and we solve for these feedback parameters. There's feedback parameters at each time leg, but we take the mean of these feedback parameters from 7 to 21 days to get a physical feedback parameter. And if we look down here, we run through this. These are our imposed feedbacks and our feedback parameters. And if we back them out using these equations, we see good agreement in the way we kind of have backed out these feedback parameters. So now we know that this strategy works for backing out the feedback parameters. So now since we don't know the feedback parameters in our reanalysis data, we can then use the same technique and back them out. We can also remove the feedbacks to come up with a system where there are no feedbacks present to see how these feedbacks affect, see the difference between the no feedback case and the actual case. We use this same equation that we started with, and it will hold when there's no feedback. So these tilde forms are just the no feedback case where we set A to be 0. And again, when we use two modes, this will be a complex matrix equation. Again, all of the A values in that matrix equation will be 0, and we'll be able to calculate a no feedback case. And we'll be able to, once we have this no feedback case in hand, we can then calculate a change in variance and see how the variance changes when we have feedback versus when we have a no feedback, and we can attribute that to the feedback that we're removing. And so we'll simply divide the covariance of the no feedback versus the covariance of the feedback system. And so what this means is that when we have a change in variance that's greater than 1, it means the variance is higher for the no feedback case, which doesn't make a lot of physical sense. It means that the presence of the feedbacks will actually reduce the variability. When the change in variance is less than 1, we can intuitively understand that as the presence of the feedback will increase the variability. And we're going to look for this change in variance later on when we do this for our seasonal analysis of the error interim data. So we're going to use error interim to run through the same process that we did with the synthetic data, because we've known that we can now back them out correctly and we can move forward with our analysis. So this data goes back to 1979. We're going to use 1979 to 2017, even if they do have more recent data. We're just going to cut it off at 2017. It comes in 6-hourly data, 4-dimensional. We're only using the zonal U and Mariano wind V, and we use V to just calculate the eddy momentum flux. We don't use it for direct analysis. But again, this is just, the benefit of this is that it's the most recent set of the ERA data. So the first thing we do is we take our U and our V that we have from the variable data, and we calculate the momentum flux, and turn that from a momentum flux into a convergence, which is M. M is the same term we were using on the synthetic data. And we convert this momentum flux, or eddy momentum flux convergence from meters per second to meters per second per day, just because per day has a better understanding of the time scales that we're looking at for eddy momentum. So just to kind of set up everything before we jump into the analysis, we remove the mean annual cycle and smooth it using a 30-day running mean. We vertically average from 1,000 millibars to 100 millibars. We don't want to deal with the effects at the way top of the atmosphere. We weight by cosine of latitude to account for the area. And we're going to perform our EOF analysis on the daily mean U, and then project the 6 hourly data back onto the mean U. So here are our results for when we run our EOF analysis. So as you can see, remember we mentioned that the jet has a center at 50 degrees south. And we see in the EOF1, we see these positive values forward of the jet, or forward of the center. And we see these negative minimum values equatorward. And this EOF1 is showing us the north-south fluctuations of this jet. In EOF2, we see it centered right at the center of the jet. And this is explaining the strengthening or the sharpening of the jet. So mode 1 explains the north-south fluctuations of the jet. Mode 2 explains the strengthening and sharpening of the jet. The eigenspectrum over here just shows how much variance is explained by each of these modes. You can see how a lot of the variance is explained in mode 1, and a pretty good amount in mode 2, and then if you continue on, there's less and less variance explained as you go up in modes. Previous studies only looked at 1, but we're going to include this one in our analysis. Just a side point here, if you look at how well in good agreement these EOF plots are throughout the seasons, we'd expect there to be possibly a little bit more variance in the throughout the different seasons. But if we go to look at these kind of monthly mean zonally average winds, we see how the mid-latitude jet here is almost always centered right at that 50 degrees south point. There is a lot of change up in the upper levels, so you may see there's all these changes, but when we're looking at the strength and the location, it's fairly consistent throughout all seasons and all months as well. So if we start, we're going to just look at June, July, August to begin. We do this for all the seasons. This is the Southern Hemisphere winter. And we can note here, we note these circles are where we're looking for these positive correlations or these feedbacks. And we note we have significant positive correlations when we correlate U1 and U2 together. Again, that's helps us explain the poleward propagation of the jet. And then again, we see these non-zero correlations show up on our range of legs fairly consistently throughout these other relationships throughout the different modes. We have, positive correlations here, some more positive, and then we have some negative correlations here. We're not going to get too far into the specifics of what these correlations mean, but it goes to show how important looking at these different modes are in the looking at the combination of these modes.
So this is daily data?
This is 6 hour data.
6 hourly data.
So it's
okay.
the EOFs were taken for daily mean U, and then we regress the 6 hourly data back onto those EOFs.
So even though those correlations are really small, you've got so much data that they're probably significant.
Right.
And it's just indicating that this effect is subtle, but it could be important.
Right. I think we found that the statistical significance was 0.03. I think,
Okay.
for the correlations to be 95% significant. So, yes, they are small, but they're important. They're not negligible.
When you have that many opportunities to integrate a small effect, it can end up being important.
Right.
Take home message.
Yeah, yeah. So then we can, as I mentioned earlier, we can remove the feedbacks. So we found the feedback parameters, they're over on the left there. Once we have feedback parameters, we can then, through the process we used earlier, back out what would be a no feedback situation. So now we can start to see what effects these feedbacks are having on the data itself. So the blue lines are the actual data before we remove the feedback, and the red lines are these removed feedbacks. So you can see here, like in U1 and U2, the persistence of U1 and U2 are much less when you remove the feedback, which again we would expect, given that there's not as much kind of connection between the two. And then if we look at U1 and U2, we see where we saw this kind of high positive correlation at these legs that we're interested in. They become nearly zero when you remove the feedbacks. And so we can surmise that with when you remove these feedbacks, those feedbacks account for a lot of that polar propagation that we can assume is occurring with U1 and U2. U1 and U2 denotes this polar propagation. If you remove the feedbacks, that becomes zero, and the feedbacks are.
I think this is the second time I've noticed this, CJ, that the maximum difference between the feedback and no feedback experiment is right around 10 or 12 days. Is there anything physically relevant about that time frame in the 12-day lag?
Not that I investigated for like.
Yeah, okay. It's sort of interesting that it kind of encroaches on the S2S time range in a way, and I'm curious about that.
That would be something to look into for sure.
Yeah.
So, and we can see here in these other, when we cross-correlate between M and U, that the no feedback case is reducing the correlations almost across the board here, in that it's bringing it closer to zero, I suppose, would be the better way to say that, because we have an M1, U2, we're bringing this down closer to zero. This is already pretty close to zero. And that's what we would expect when you remove the feedback, is that these correlations at high legs are going to be near zero. We also include here the change in variance. So now that we've calculated a no feedback case, we can calculate the variance for the no feedback and divide it by the feedback of, or the variance of the actual case. And we get this change in variance. Now, it's not the most intuitive way to understand this, but if you, so this, what this 0.69 ELF1 change in variance means is that the feedbacks account for, or increase the variance by 30%. The feedbacks are accounting for this 30% of the variance in ELF1. And in ELF2, they're accounting for 33% of the variance, which is a significant portion. When you think about this, the feedbacks are having a big effect on the total variance. So again, we wanted to emphasize how important it is to use coupled versus uncoupled data. Previous studies used the uncoupled data, we're using coupled. And we can do this fairly simply by running, by setting A12 and A21 to 0. And the feedback equation simplifies from what it was before to what it is now, where A11 only affects itself with mode 1, A22 only affects itself with mode 2, because these are independent of each other when you're using the uncoupled situation. And we can plot these together, and we can see that when you use the uncoupled data, now the actual is the original data, the red line is no feedback, but it's still coupled, and then the yellow line is the no feedback when it's uncoupled. And you can see that the no feedback uncoupled doesn't actually bring down the persistence as much as the feedback in the coupled case does. And that's the same for both U1 and U2. And we actually see here in U1 and U2 that when you use the uncoupled data and remove the feedback, it actually stays as a positive correlation at these legs where previously we understood that U1 and U2 are the polar propagation. And so it's peculiar that when you're using the no feedback uncoupled case that it still appears there's a polar propagation, but we wouldn't expect that when you're using the no feedback case. If that makes sense.
So the difference in the uncoupled case and the no feedback case. In the no feedback case, you estimate all of your parameters, assuming a coupled system to just zero off the off diagonals. Whereas in the uncoupled case with no feedback, you're estimating the parameters assuming an uncoupled model. So A11 is actually different than the coupled case. Is that correct? Got it.
Yeah.
Thank you.
It's a completely different calculation, but
Yeah.
And so there's some significant differences here. And then when you look at the change in variance, the difference between the uncoupled and the coupled becomes even more clear. Whereas before, the EOF1 and EOF2 feedbacks were, in EOF1 and EOF2, the feedbacks were accounting for anywhere from 30 to 33% in this June, July, August time. Whereas now they're accounting for 5% of the total variance. So using a coupled system is very important when you're looking to see how this affects variance. And again, I won't go too.
Sorry, one more question here. From the previous, so you're calculating those autocorrelations. How do you calculate those autocorrelations? Do you run your model forward and then calculate them, or what do you?
How do we do like autocorrelations?
Well, I know you calculate autocorrelation, but
Well,
what, I mean, like in the case of the no feedback case,
Right.
how are you calculating your autocorrelation function?
It's the same way we did it for the no feedback case. We just changed the feedback. We changed the feedback parameters in the system.
And then you just like run a synthetic time series forward or something?
Well, explain it.
I'm sorry, if I
No.
like for U1 there, I mean,
Yeah.
that blue is just the principal component autocorrelated with itself, right?
Yeah.
So and so that makes sense to me. When you get rid of the feedback, what are you removing from the principal component?
So for the blue line here, that's so we have this U that's just in our data as it is. Like that's the raw data. We run the autocorrelation of that U, right? Okay. So when we do the red line, which is the no feedback case, we remove the feedback and we have this new U value, this U set of points, which just does not have a feedback in it. Right?
So you're working with ERA interim data now, right?
Mhm.
So when you remove the feedback, how are you calculating the new U1?
When we remove the feedback, so we go through kind of a lot of steps to back out the no feedback case. Is that you're wondering how we go from regular to no feedback?
Either.
Okay, so when we go from, we go from like actual to the no feedback case. Okay, so we have our U calculated. We calculate our feedback our feedback parameters. Then we take those feedback parameters and we set up a new equation that solves for the no feedback case now that we know the feedback parameters. And then we have this new U, this new no feedback U.
That's what I'm wondering.
So this is a pathway from the ERA interim data to a synthetic data set, which is calculated with the removal of the feedback, is that what's going on?
I suppose you could look at it that way, because right, so we have the initial era interim data, and then we calculate the feedbacks. We remove those feedbacks, so now we have this new kind of set that has no feedbacks.
That's what U1 and U2 would be were there no feedbacks, by your estimation.
Right. Do you want to explain?
Yeah, probably go back 3 or 4 slides or something, or yeah, maybe there even, or wait, go back one line. Yeah, that would be good enough for this, like one. So you find A, and then using A, you first find the new M as if there was no feedback. And then you use the budget equations that you usually think, and then find all the other things from that. So you from the lag covariance, you find A, and then you find the new M, and then you have a relationship between U and M that you use. You don't actually have to make a time series, you can just do it like in 48 space.
Oh,
and then
okay.
transfer it.
Nice, yeah.
Yep, that's what he did with that.
Thanks.
So we can look at the kind of persistence for both EOF1 and EOF2 and how it looks from season to season. And we can see here that in EOF1, the correlations drop down whenever you remove the feedback for every season in EOF1 except for March, April, May in the uncoupled case. And in most cases here, the EOF2 persistence drops down and is reduced when you remove the feedback parameters, which we would expect, because there's no feedbacks there to affect it. Again, we can look at this for U1 and U2 when you couple these, or during these, the coupling here. When you remove the feedbacks, you reduce the correlations, which again, we understand, that makes sense to us. If you remove the feedbacks, you should be bringing this down closer to 0 in the 2 cases where you remove feedbacks.
But even the no feedback uncoupled case, you still do get overpropagation.
Right, which is concerning that it's the uncoupled case, because we wouldn't expect that to be
Yeah.
right, because if you're,
That's the way it has to be, because they're coupled, but not taken into account, so they're still going to be coupled. You're doing the feedback analysis individually on each one,
Oh, okay.
and so when you remove it, you still have that obligation there.
But it's not being captured by them. But it's not being.
It's still there. You haven't considered them to be coupled.
But if you were to take your model and integrate it forward with like a synthetic set of data, like, so this gets to the question of how did you get U, right? If you were to do this using synthetic data with no feedback uncoupled, then you wouldn't see that whole propagation anymore.
Yeah, but, I mean, they are coupled in the atmosphere, so that's why you get, and if you treat them as they are uncoupled, you get this sort of unphysical thing where you still have propagation and there's really nothing to cause it anymore. You need friction won't do it. It has to be the eddies, but you didn't take that into account.
Okay, so this is not an indication that, there's 2 ways you can make the plot. One is by what you did in order to calculate the autocorrelations and all this stuff, which is to try and remove the effect of the eddies from the couple R2, so to try and fit your model to the actual data. The other way of doing this is to take your model and iterate your model forward, like you did at the very beginning. In that case, you wouldn't see a non-zero correlation in a couple of cases.
And no, you would, because the M's would be coupled, you didn't remove that part.
Oh, okay. Okay.
so we'll look here at just the change in variance when you look at the coupled versus uncoupled. And again, in EOF, that's just a reminder of how we kind of calculated that change in variance on the lower left there. But if you look at, for EOF1, we can see that in the coupled case, The feedbacks can account for anywhere from about 20% to nearly 50% of the variance, the zonal wind variability. But when you have uncoupled, you have these values that get above 1, which means that the feedbacks are then reducing the variability. Which again, just emphasizes why it's important for us to use the coupled case and not the uncoupled. And we see similar results down here with EOF2. We have these values below 1, which means we're increasing the variability with the feedbacks. But uncoupled is greater than 1, and that's reducing the variability with the feedbacks. So our first conclusion is that using coupled feedbacks is necessary because we see if the coupled and uncoupled cases were identical, there'd be no point in using the coupled case. If we could produce the same things with uncoupled, we could leave it as is. But we clearly find there are big differences between the coupled and the uncoupled cases. You see it very clearly in the change in variance, where we saw that the change in variance greater than 1 means the presence of the feedback reduces variability. And again, here just goes to show the difference between the uncoupled versus the coupled. So when we're solving these feedbacks, we need to account for the coupling. We showed we were able to identify the feedback parameters, or identify the feedbacks through these correlations. And we see this polar propagation in U1 and U2, and we see these correlations at these lags of 7 to 21 days that we're looking for, but we're not going into too much depth as to why we see those. Found we were able to quantify the feedback parameters. And again, feedback parameters are in per day. And there's, the feedback parameters are, they all agree in their signs. So we have these A12 is positive, A21 is negative. Again, that's another sign of this polar propagation. And again, they may seem small parameters when you're looking at, on the time scales we're looking at, which are anywhere from 7 to 21 days. These small parameters in per day can get big and have big impacts. Kind of the final point here is just how feedbacks have a significant impact on the zonal wind variability. And we can even see here in, like, for example, in June, July, August, the feedbacks account for over half of the variance, or half of the zonal wind variability just in the feedbacks. And these feedbacks are having a big impact on the variability in our system. And it's important to understand them. They can change quite large. I mean, we have big changes where UF2 in DGF only increases by 4%, but again, there's still this increase throughout all of our feedbacks. So again, I just wanted to thank everyone who helped with this project. Dave, spent many hours with him going back and forth, trying to figure out how's the best way to kind of show all this stuff, and just, he's really helped me out a ton. The committee, Dan and John, for giving up their time to read a thesis in the end of the semester when I know it can get quite busy, so I really appreciate that. All the AOS staff, all the ladies in the office who have helped kind of keep me on track. Fellow graduate students, those of you here now, those who have graduated have all been really helpful. It's a great support staff, or a great support group to bounce ideas off of and just talk. And if it means just getting out and going out and having a drink, that's just as important as what we do kind of in the office. Family and friends, a few of my family made it out for this trip. My sister, my mom, and my aunt all made it out. I'm really appreciative of them for coming out. And then my wonderful girlfriend Nellie, who couldn't be here today, she's doing field work, but she's been very supportive and wonderful throughout this whole process. I want to thank them for all their help. Any questions?
So the physical interpretation of these feedback parameters. Can you give us some insight on that?
We didn't go into too much depth as to what what each parameter means, each term that we have. We have these 4 feedback parameters.
Well, so I mean, your let's see, A12, right, is
Right.
the role of the second EOF in influencing the noise that would force the first EOF,
Yes.
right? So maybe A21 is the easier one for me to think about. A21 is the role of that shift in
Mhm.
influencing the extension,
Mhm.
right? So the shift of the jet's gonna cause eddy activity to shift with it, right? So if you have a northward shift of the jet, eddy activity would shift with it. And then A21 then is the role of that shifted eddy activity in influencing the extension, or the kind of the narrowing, widening of the jet. So why does that happen?
Why are they, like, paired together like that?
Yeah. Why would one term be negative and why would one term be positive?
Well, I think by convention, they have to be positive versus negative.
I mean, you showed that one of them was negative, right?
Right, but those two terms, like, they can't both be the same sign.
The fact
If
that,
it-
yeah,
yeah.
the fact that opposite signs have some sort of propagation,
Right.
and the fact that the A12, I think, is one's positive, versus the other one is forward propagation instead of equator propagation.
Let's see.
It's what's in the A12 is what's important to making like
1,
stronger
2
jets
is-
shift forward, which is like what climate change is about, like you're just reinforcing it makes the jet stronger, but it also shifts forward, and that would be the A12 acting.
Yeah, but how does that happen? That's
So
what
like the actual mechanisms.
Yeah, yeah. Is there
CJ
anything?
didn't go- Yeah,
Okay.
yeah, that's some other papers.
Is this, well, is this possible that as the jet strengthens at a given latitude, it sets up a higher incidence of wave breaking? Is that a possible mechanism that then pushes the jet forward, so that's why there's that connection?
What it is a stronger jet becomes more reflective on the forward flank, which means you tend to get wave copying, which is momentum flux in the opposite direction. So it's basically, it's sort of, doesn't even involve braking explicitly, it's actually sort of a linear wave phenomena with just turning latitudes and reflection.
Oh, okay. But how, well, okay, here's this follow-up question, it's not maybe included in your study though, but it's in the, we're not gonna have a committee meeting after this, or are we? I don't wanna know, oh, so I'm gonna ask my questions now, okay,
Yeah,
so.
we could have a committee meeting afterwards either way, but.
So here's my
There's
question.
GSA meeting.
Well, what's the synoptic manifestation of those kinds of processes? It might not be in your study, but I'm interested to know. What's the most frequent synoptic structure that reflects that?
Yeah, so like when you have a stronger jet, you tend to have waves tilted, like in northern hemisphere, these northeast to southwest tilted across the jet.
Yeah, so those are the right ones for poleward momentum flux?
Yeah.
Yeah, okay, that's what I was
Yeah,
wondering
that's
about.
what
Okay,
we-
so that's the way one thinks about it.
Yeah.
Okay.
I think, as Michael was pointing out, that, it looks like you're really looking at the subtropical jet as opposed to either one. When you look at your jets, they're centered up about 200 millibars, which is pretty high for the Bear Clinic or polar jet. So there seems to be some, the fact that you're kind of lumping these together as a single jet. I wonder what it really means, that perhaps this interaction between the existence of the two jets has something to do with this movement, which I still haven't reconciled in my mind what this really means, but it must mean something, because I think the two jets are there for two different reasons. And of course, seasons change the emphasis of what you would get for the two different jets. Now, this correlation you get, what happens with the subtropical jet is when it pushes poleward, that has to do with the push of this tropical air, this tropical plume. It's carrying air at high levels, around 200 millibars poleward, and creating a plume of this low potential vorticity, very cold polar air at the tropics, but very cold tropical air at the high levels is pushing it poleward in these plumes, and then that affects the way the polar jet develops. So, I don't know, when you group them together, it seems to take the physics out of it, that I'm having a hard time understanding what it really means. Somehow blended into what you're doing.
You show your EOF structure and how it's unsensitive to like the mean state, so and it's like the mean state, the only part of the mean state that's fixed is really the mid-latitude jet. But your EOF structure and all those different seasons almost doesn't change.
Well, you
So
know,
like, at least for this problem, it's like this is picking out of like mid-latitude jet variability.
but the mid-latitude jet doesn't really extend with high amplitude up to 200 millivolts.
Can you scroll forward one?
It's mostly below that.
So are those EOS 200 millibar, or are you taking the EOS and the zonal mean flow?
He's taking EOS and vertical average.
So the vertical average averages out the subtropical jet and the size of the mid-latitude one.
So it would seem to me that what you're looking at is somehow the semi-permanent extension of the subtropical jet into polar latitudes.
But if it's a vertical average, he's averaging out the subtropical, I mean, not completely, but he's averaging out most of that subtropical jet, right?
And like
I
in
don't know.
January, there's no subtropical jet hardly at all. It's at 50 degrees latitude, it's not really a subtropical jet, that's mid-latitude jet pure in January. And then in July, you got a subtropical shoulder jet that's got the strongest winds at like a point, but in the vertical average, you actually have stronger winds at that, again, with that mid-latitude jet.
If you look at the zonal average, you're gonna see the most persistent.
You know, it seems that when the subtropical jet, just watching this synaptically, when the subtropical jet is pushed into the polar latitudes, it develops a lower branch to it. It develops, it moves down because it creates baroclinicity at low levels through its circulation, and this actually creates a lower part of that jet. So ultimately, if you push a subtropical jet into the polar latitudes, it becomes a polar jet after a while.
Yeah.
And
So I guess my distinction, the way I think of the mid-latitude jet is predominantly eddy-driven. When you get the winds going to low levels, it's because of the eddies. You can actually do this through the budgets.
well, that's consistent with the eddies being largely forced by tropical plumes that drive the subtropical jet polar.
Not necessarily.
Not necessarily, but
It could also be eddies
it may be
developing by
related.
baroclinic instability, right?
What's that?
It's also just eddies developing by baroclinic instability, depends on the slant of the eddies, right?
Well, at the upper levels, you very seldom see return cold air. You mostly see plumes of return warmer air. You mostly see plumes of colder air going poleward. The return flow would be the lower part of the Hadley cell, or the lower southerly push, so that at high levels, it seems to be mostly plumes of cold air coming out of the tropics. And, you know, these create the arc subtropical jets, and eventually you get eddies along that. And then those eddies can become waves that have equal transport north and south, or transport one way or the other. But I think the tropical push is the driving force of this whole thing.
Is it also true there's a little less variability?
In the Eddy model, you get
He's
get
looking at the
momentum
you get baroclinic instability without any tropical
So it's the eddies
plumes.
that are doing this.
So you could definitely get baroclinic instability
Region of
without
those EOS
those plumes.
that expand
and
the
you
EOS
need to
there.
It's
surface
mostly
winds.
tropospheric baroclinic instability.
I'm
We should try, yeah.
maybe we should take this conversation, unless people have other questions for CJ.
So thanks, CJ.